Science expects that you conduct background research. This leads to defining the purpose and an objective of an experiment. The overall goal of a scientific investigation is to, well, answer a question. So, our observations, questions, research, they all have already been found out by somebody else who could have potentially asked the question already. We want to get close to defining our purpose, and that's why we conduct background research. It brings us closer to our purpose or our objective in our experiment. And a statement that clearly shows what question you are trying to answer in your investigation is what the objective is, or the actual purpose of the experiment. Now, constructing a hypothesis has many biased definitions, but a hypothesis is, what do you think might happen? It's a testable prediction based on your observations. It's way more than a guess because you've done background research, so you know you expect to see something. And it describes the cause and effect and the relationship between the variables that you're testing or collecting data on. There's usually a format for this that we teach students. That's an if-then statement. If my independent variable, which is my cause, then my dependent variable or my effect will happen. Determining and defining these independent and dependent variables can be tough and challenging. An independent variable is what an experiment will deliberately change or manipulate in the investigation. Oftentimes, it's usually on the x-axis of a graph. So the x-axis is across, right? Usually it is, but not always. It should really be the only thing that's different amongst your groups. So if you have multiple different groups in your experiment, look for the thing that is different or changing. That's often your independent variable. It is independent of everything else in the system, in the experiment. What's happening to that is independent of all the other factors. If you want to do an experiment to see if what you drink before a race affects how quickly you run, what do you think is the independent variable in this statement right here? A dependent variable is depending upon the experiment that you've chosen. It's what changes in the response to the independent variable. So usually along the x-axis, oftentimes we have time. And on the y-axis, up and down, we have something that changes. And so oftentimes that's the dependent variable. The change here is depending upon this factor right here. And it usually represents by data that we collect, and it's oftentimes measured. So recall the running of that experiment. What's the dependent variable? In any experiment, when you want to test a hypothesis, you're going to need materials to do that. You're going to have to include amounts of things that you need, the brands that might also be important for some things, and be as specific as possible. You want to write a bulleted list of chemicals or equipment, other things you might need. When you write out your procedures, you want to be specific. Start with things that are action words and include every step so that someone who is reading it can duplicate what it is that you're trying to convey. What did you do in your experiment? If I want to reproduce it, what procedures do I need to follow? It's very important when you're designing your experiment and your procedures that you consider, what's my control group going to be? Because this is like the normal conditions of the group. It's a group that's used to compare your experiment with. We have to have some sort of control that gives us a baseline of what to expect if we weren't experimenting. And an experimental group is the groups that you're going to be testing. So what is the experimental group in that running example? And what would be a control group that you would give in that running example? Anytime you run a procedure, you want to consider constants. The aspect of an experiment that are held constant and consistent. You want to ensure that all aspects and trials are identical except for the independent variables. Those are the things that are changing. And you want to ensure that any difference measured in the dependent variable is only caused by the independent variable. So, all runners should be the same age, gender, same breakfast that day, same training, same shoes, etc. And have it repeated trials. Try to repeat as many as you can to ensure that your results that you get are not due to chance. You want to eliminate as many errors as you can. So here we're going to analyze the data and the results of our running situation in our experiment. So results, you're going to collect all the data from and organize it in an investigative type of fashion, like a data table or a graph is always acceptable. And then you want to present the data in a very easy to read way, like a graph where things just kind of stand out. You don't want to act like you're hiding anything from your experiment from your reader or your fellow scientist. And then you want to analyze it. I only make statements about what the data shows. Don't make any inferences here. We don't want you to infer anything. We want you to talk like a cookbook, very straightforward to the point. Highlight any patterns that you might see in the data and discuss any potential errors that could have been collected. Here we have our independent variable, which is time. And then we have our dependent variable, which is the number of substrates that reacted in our model of enzyme-substrate interactions under various conditions. It looks like we had our control group, which was trial 1, this dark blue one right here. That's our control group. It established a baseline. And then in trial 2, and then 3, and then 4, we had different numbers of substrates that reacted over a period of time. Anytime a scientist draws a conclusion, you need to be explicit in your statement. Don't hem and haw about it. Make an explicit statement about whether your hypothesis was supported or it was rejected based on your experimental data. Data may support your prediction. It also may reject or fail to support what you thought was going to happen. Data does not prove or disprove anything. It's describing any real-world application that can be used for the information that you learned for the investigation. Basically, leave a little meat on the bone for other scientists to pick up where you left off. Now might be a good time for you to practice scientific investigations and read each scenario and answer the questions to the right. You should have this assignment inside of your packet. Science is quickly advancing. Science, that's really what it stands for, the advancement of knowledge. We need to answer questions based on observations that we see around the world. Technology has really helped us in this. It's the advancement of society. It's solving a lot of problems based on all these needs that we have in our society. And it's the application of scientific discovery that in order to meet the needs of all the humans and the goals that we have in our lives, we need to develop a product and a process. And we call that product and process, when we use technology, engineering. It applies to scientific and mathematical principles that are used to solve problems. The engineering design process can be slightly different from everybody, but it basically has these major components. Technological design will involve clearly identifying and defining a problem or a need, whatever the case may be there. And then a solution, brainstorm, research, sketch, find something that you might think could be a resolution to this, all within the constraints of things. Engineering has another application to science. There's no limited funding for this. So in engineering design, we want to be cost effective. We also want to be time effective because we all know how much society hates waiting for things. And also consider materials and availability. And nowadays it's popular to be environmentally conscientious when you're doing something. The perfect design is never really possible, but you have to highlight the benefits of it. And then of course the risk, like could it be too expensive or just take too long? Once you have your design solution, then you want to build and test. You want to implement something where you can continually make improvements. And then evaluate it. Sometimes it's evaluated by your peers or yourself or others.